Ödül töreni programımıza Arçelik Türkiye 2015'in uluslararası jüri üyesi olan Alexandros Kallegias'ın sunumuyla devam edeceğiz. Kendisi kendini tanıtacaktır. Ben herhangi bir şey söylemeyeceğim. Eğitimci, uygulamacı kimliğiyle konuşmasının konusunu da bu iki alan arasındaki ilişki üzerine vurguladı.
Second. Lower the lights, please. Thank you. So I would also like to thank you very much for the introduction, Dr. Lalos. Also many thanks to Dr. Nur Çaklar and Selim Vanli for inviting me here, as well as the sponsor, Sarah Samank. I'm honored to be here. So my name is Alexandros Kallegias. I'm a senior architect at Zaha Architects, a BIM coordinator in one of the leading projects in terms of BIM in the office in the UK. I'm also the director for the AA visiting schools in Greece. I also co-direct the Architecture Association Summer D-Lab with Dr. Elif Erdner in UK. And I'm also involved in the tutoring team of Dr. Elif Erdner's AA visiting school in Turkey. Part of my background involves University of Liverpool. Today I would like to talk about academia and practice. So, a little bit more about my background. I'm not sure if you can read this. I hold a master's degree in architecture and urbanism from the AA Design Research Lab, where my theme was, my master's thesis was about robotics and architecture. In that regard, computational design and digital fabrication have been following me for all the progress that I am involved in terms of the AA visiting schools. And that comes together with the work I do together with Zaha Architects. I'm going to briefly talk about the office that was founded in 1979, so more than 35 years. The office projects vary from opera houses to house projects, theater to furniture, cutlery, working in all different scales. But each one is customized to its requirements, and this relates to the construction process and the design then. Right. Should work. It moves here, it doesn't move there. Right. So the office operates in different parts of the world. What is important is that we always try to deliver each project with the same quality while maintaining a unique character. I will try to give you an overall impression of how the office operates and how tooling and collaboration are critical points of the workflow. and how the challenges are kind of overcome through this. And I will focus on one particular one, so I'm going to briefly show you a few of those, starting with the Allied and Edith Road Art Museum in the US. You will probably see more of it if you go to the movies. Here the challenge was to conceptually fold the varied circulation and visual connections. There is a challenge on having a communication between the landscape and the building, considering the circulation of the people inside and their viewing points. So I'm going to be very quick. I would like to show you quite a few. Here we are having an example of how clear glass facades allow light to flow through the main exhibition space of the Glasgow Riverside Museum. So the museum is open at both ends. The outline wave symbolizing the dynamic relationship is quite important, and all this is in order to achieve a communication between the harbor and the city. Another example is the project in Gwangju, China. Its contour profile, the unique twin boulder design, is again another attempt to, another approach to enhance the urban function that opens access to the riverside and the dock areas. Moving on to what we see as an example of customizing the design for a local symbolism in China. This symbolism relates to having good luck, and it's actually a statement of the city of Nanjing in order to have a lucky Youth Olympic Games. So it's unfortunate you cannot see some of the information here. This was finished in 2014. Just going to show you a few examples, and I'm going to relate to them all together. Now, this is the Port House project in Belgium. This has been, it's located between the city and the harbor. It has a symbiotic character. What you see below is a listed building. So at this point, coordination level was high because we had to coordinate together with various local consultants and mainly authorities in order to achieve the permit for this kind of structure. Another example of a symbiotic sort of relationship, not so much symbiotic, but perhaps, let's say, a challenge of adaptation to an existing structure. This was a moment where the actual slabs and columns and everything was there, while we were faced with the challenge to introduce a sort of unifying design for the internal as well as the external architecture, both in and out. For those of you who've been in London, you probably recognize the London Aquatic Centre. This was inspired by the fluid geometry of the water in motion. Again, adaptation, maybe not visible here, but for those of you who were there during the Olympic Games, you would know how, besides the design being consistent within and without, outside, it was able to accommodate more seats. So all these aspects are taken into account, and there's always a certain strategy on how to maintain the aesthetics of the office and being practical and following the regulations. You probably recognize this one in Azerbaijan, Baku. This is a fine example of complexity and all the challenges that are inherited into what we call a state-of-art project. Now, the main challenge was here how to manage to construct such a large-scale project, a continuous sort of impression of an outer skin facade, and how to include this includes various different programs underneath. Besides there's library, there's an opera house. For those of you who have been there, you know. So there is always a need to, or let's say there is always an intent to have a fluid approach, also in terms of the design as well as the programmatic brief. And all this actually are possible through the tools that we use in the office, and I'm going to explain a few more things in the next project in detail. Now, these tools help us realize certain aspects of constructability. When you design something on your machine, on your computer, for the younger architects, it's always a nice feeling to go beyond the things that you might think are constraining you. And this is quite important for us as well. At the same time, we have to be aware of reality, and we try to push certain boundaries, achieving this sort of approach. Now here, what is not visible so much is that when you kind of come together to propose such a building, then you have to understand how you will coordinate the fact that you have to take all the way to the top this part, for instance. So together with the rest, together with the fact that you collaborate with other consultants, you have to accommodate the time, the effort. So put things in certain sequence. This is an example of quite a few projects in the office where we have an outer surface covering the internal, let's say, the interior, the programs underneath. And in that sense, one has to consider how the connection happens when it comes to the interface between the outer envelope and the inner structure. And of course, when we talk about scale, just look at the size of this person and you will understand how this is one of the biggest, the largest cranes in Baku in order to achieve this sort of architectural project. Now, together with this, we have a lot of drawings. This is just very early examples. What I want to focus your attention to is the fact that not only the building is part of it, but there's an interest in having an urban, let's say, impact on the city. The city of Baku it's mainly characterized by, let's say, projects that don't really invite people in. The city itself, while quite large and open, you have barely any witnessing, any people going out, and we wanted to kind of invite the people onto this landscape, which we engineered in order to be quite consistent with the rest of the building. And in fact, there was a successful point where people were actually coming in. And there's always like a continuous theme about how you resolve the planning itself. Now, I'm going to go into the theater of Rabat. This is in Morocco. We were hired by the Agence. It was basically the King of Morocco. So this is an 1800 seat theater with 7-person amphitheater and experimental performance stage. Now, when you look at this image here, basically this comes first and then you have the rendering. But in order to achieve this sort of design, you have to be quite rational. You have to have a specific, clear mind in how you achieve this. It's because at the end of the day you want to fabricate it. So in that regard, this is based on a 3-dimensional grid, and every point that defines the trails and curves is described. So that's enabling us a coordination between the interior programs and the internal structures. Again, the tooling here is quite crucial for us, especially when it comes to changing things after coordinating with consultants. And when it comes to special typologies, special building types, such as an opera house, for those of you who don't know, this is quite a complex type to resolve. You have to make it transformable as well as performative in terms of insulation, lighting, temperature, stability, so on and so forth. And those of you who have built a theater before, you understand that there is the front of house and the back of house. Of course, you have to understand how the flow of people occurs. While for some it might appear that this is just following the initial curve design, I have to tell you there are a lot of iterations happening, and mainly what's taking place is a constant, let's say, conversation with our consultants, which is quite often the case for many, many offices. In this situation, changing the design of a curvilinear, let's say, building might seem for some might not seem a challenge. However, keeping everything in line with the regulations, with the design intent, not losing what you initially want to as an architect, is an extra challenge on its own while trying to make the timetable. So in this regard, it was the first attempt of using what we call BIM software. Again, just to briefly describe BIM, is basically building information modeling. Building information modeling is a form of collaboration using software platforms. In fact, there are levels of building information modeling, level 0, 1, 2, 3, and all the way to 6. Just to give you an idea about what is BIM 0. BIM 0 is first-year student, just using CAD, and not really, there's no collaboration basically. Actually, it's not even CAD. It's basically using your pen. BIM level 1 is using your CAD. BIM level 2, I will show briefly soon. And in this case, BIM level 2 was all about having a coordination among the MEP, the mechanical and electrical parts of the building, the structural side, making sure that everything goes well in terms of insulation and the seating and the acoustics, while having our design intent happening the way we want to. Things that are not very clear here is that we always run simulations that we talk about in terms of academia soon. Simulations in order to make sure that we are following regulations for the fire department in this situation. Because when you have 1,800 people inside the building like this, you have to be able to take them out very quickly, as most of you understand. So when this is a transformable place, in order to exhibit different things, you have to understand that if a car gets on fire, you have enough time in order to get everyone out. And that happened later on the design when we had to introduce certain openings, certain escape routes. So the whole design had to change. And that was quite a challenge, which we successfully managed thanks to the tooling that we used. So now I'm going to talk a little bit more about this project, which is in Saudi Arabia, the King Abdullah Financial District Metro Station, which is part of a larger scheme as an initiative of King Abdullah to connect the airport with the financial center of the city. He wants to regenerate the city and has placed projects around there. One of them being iconic, has been assigned to the office. So this is actually a leading project in that regard of using BIM. Because being iconic, that means we have to be consistent in terms of interior and exterior. We have to have a clear understanding of how it works, how it comes together, and how we collaborate with our consultants. We would not be able to do anything if we didn't have our consultants on board. We are able to successfully complete projects because we communicate, and we always have kind of close working relationship with our consultants. So just to give you an understanding on how things happen, as an architect, you start having your initial design intent in your machine. So what that means is you basically have to break it down for your, let's say, BIM coordination. You have to break it down into different parts. And in that sense, you become a bit more efficient because then you have the ability to subdivide the tasks and assign things, and you become more efficient. Again, it's a matter of collaboration, coordination within the office itself. So we recognize different models: facade model, internal facade cladding, internal freeform geometry, if you like, structural model, landscape, and MEP model. These are just basics which are everywhere. However, in terms of approaching a project here, there needs to be a clear division because some of those are being directly coordinated by our consultants. So what that means? That means not only you have to face certain aspects on how to communicate through the tools that you have in your hand. How can you talk with someone in Saudi Arabia while you're in United Kingdom? How can you do that efficiently in terms of time and information that you send abroad? And that comes in the form of a page, let's say, that not only includes information about what, let's say, the file includes, but also the history of the file and what has changed. And this is very important because eventually you end up having a lot of feedback directly as soon as you refresh, let's say, the collaborative model. We're working in Revit, by the way, but that's a detail. There are a lot of BIM modeling tools out there. So you get to have these sort of things in front of your machine. For those of you who will start their, professional life, this might not make sense, as you were probably exposed all the time in order to draw, in order to make drawings, in order to have lines and renders, not a bunch of text. However, this is a crucial part of every project's successful delivery. And in terms of BIM, this is one of the main crucial points to consider. And things that you probably know while studying architecture, when it comes to, let's say, having a project origin point, you may have it, we have to understand again the tools, because in that regard, you may start by setting it up. So this setup, when it comes to the collaborative character, this needs to be introduced at the beginning, from the early moments of setting it up, because these basic constraints will always follow you. As soon as you break it, then things will probably go the direction that you would not like. So simply, this is, I don't know if you can see it, this can be considered like an origin point, and when you go through different software, you understand that this has a direct impact, because you have to understand how to use this software to communicate among themselves as well. And if that doesn't work out, then there is always a case of having uncoordinated work, can result in headaches, trying to put together the various different discipline models. This comes down to not know what other disciplines, not knowing what they do, but also how they do it. So there was a moment where we had this issue, where we had to realize how this came across and how we can fix it. And the coordination needs to be applied in different parts of the project. This is setting up, for those of you who work with BIM, designing a three-dimensional model will provide you with a 2D delivery drawings. So you have to set these things up immediately. If you want to move from this Revit, let's say, software to CAD, you have to understand how the translation works. Pretty much the way that I have to learn English in order to communicate with you are the basic things of having build-ups, wall build-ups, floor build-ups, all these things that you learn as an engineer, maybe, as an architect engineer, now come into play, and they're actively used by the software. Because as soon as you put this inside and you set it up correctly, you can actively change all the aspects of the projects, while at the same time have a direct report out for any kind of use you want. Setting it up requires knowledge of the tool itself, requires the knowledge of the restraints of the tool and how you can move around it. I mean, often we tend to not only solve design problems, but we solve software problems, let's say, in order to include the metadata, as we call it, into our design files. Again, it's a matter of communicating with our consultants and everyone else, even the client, in order to have a coherent, let's say, approach to what we intend to do in a project. The ability to hack the software then becomes part of the workflow, and we can assign all different attributes to our design elements. That would include any internal cladding that comes with certain aspects of construction that can then be delivered directly to the contractor. But this is another level in BIM. Crucial part also is the uploading of files. This is more like the cloud, as you might have heard. You put things online, you put things on, this is crucial, because you eventually now have to feel comfortable of uploading your files. And you have to learn how to collaborate with people in a different way, not in the way that most of the architectural practices have done so far, but you have to know how to set up certain parameters, certain collaborative parameters, not security so much, but how much information is given and when. So these are aspects that are not usually seen, but every architect should be aware even before they start their professional life. So what is behind the scenes is always a workflow, and understanding that workflow will make us more efficient. Just briefly, I'm going to describe how it usually works in, let's say, the building information modeling approach. You have this shared area, as we call it. Specifically, this is online platform called ProjectWise, how we do it, we have different models, the structural, the architectural, the MEP, that are being informed by us, by our consultants, and eventually this is uploaded and delivered directly to the client. Now the client becomes almost like a watching person, always having a constant, let's say, report. This, again, might make a lot of people nervous. As soon as you have everything set up initially correctly, you have no worries. Actually, it becomes very efficient. And I talk by experience. However, and I'm coming to close of my first part, I just want to mention that, yes, there are tools out there. Yes, it's important to collaborate, because as far as architecture history goes, the architect in the Renaissance times was considered to be everything. He was the designer, he was the builder. Eventually, with the Industrial Revolution, the disciplines got divided. However, nowadays, there's an interdisciplinary approach again for the profession, but that doesn't mean that we have to become engineers, structural engineers. We just need to be aware about the totality of a project. Because at the end of the day, it doesn't matter if you're using AutoCAD, Excel, Revit, because once those things were not there, and still projects were being built and designed. Now, I'm going to move away from this and talk a little bit about academics, and this is how I will try to make that connection, try to bridge that gap between academia and profession. As most of the professional people in here are aware, there's a gap that is bifurcating and kind of becoming larger and larger. So in an effort to kind of inform about these aspects, with the Architectural Association programs that I'm directing and I'm involved in, there is this initiative of not having a, let's say, software design workshop, but more of a complete introduction to certain methods, certain approaches that are quite progressive and are quite actively used in different disciplines, different offices. I'm going to try to make this move. Okay, my computer is crashing. This happens, Right. Again, I'm going to briefly show a few of those, but then I'm going to focus on the work of the one in London. I'd like to play a few videos. They might be too heavy. That's why it's still not doing it. What happens is we come together with other schools and we try to kind of introduce a collaborative approach in terms of working, allowing both tutors and students, participants, who most of the times have their own business, come together with different backgrounds and try to achieve, try to resolve an architectural problematic with the use of new tools. This will not make, it doesn't follow my instructions. Yeah, my own tools don't work, but I will try to. All right, so my computers are not that great. It's crashing again. I'll try to make the time as well. That's why I'm a bit anxious all the time. So I will try to skip these parts as they are being too heavy. Okay. To put it in a short description, okay, it works. the program at in Greece was skipped because the video was too heavy. This is what was completed in Turkey, in Istanbul, with Bilgi University. The director is Dr. Alexandros, as I mentioned. And now we are coming to the point where we introduce this aspect of not just designing and keeping the design within the computer, but learning how to realize into one-to-one scale through the use of prototyping, through the use of digital machines, through the use of computational software. Now, this might sound as funny words, but at the end of the day, we keep the same sort of thinking. We have a design problematic to resolve, and we try to achieve it just using new tools. And in most cases, those new tools can actually provide us with an innovative way of thinking, which I will introduce you now. In this case, we were using vacuum forming, as well as more conventional, let's say, tools, laser cutting and CNC machining, in order to achieve what was, again, a symbiotic relationship between an existing wall and kind of a almost like a parasitic, let's say, design construction. It's quite intense. This was put together under a week, in less than a week. In fact, the actual fabrication and design was put together in 5 days. And these are the aspects of tools that can make us go faster, as long as we understand how to use them and as long as we understand how we can collaborate in that regard. My presentation file doesn't help me. No. I'm gonna try to move on to the actual part. So understanding the tools, I understand that this moment is quite an awkward moment because the actual video files are too large. This is a recent work completed in Thessaloniki, in the Aristotle University of Thessaloniki, where, again, the outcome was realized in 3.5 days. We are always keen on realizing our design intention into one-to-one scale prototypes. This is not to be considered as a final result, but more part of a research process. So during this work, those prototypes usually are characterized by interactive let's say, aspects. This is kind of a field that I'm interested in, and I always apply to the programs that I'm involved in. If it will move, I can show you. The actual approach involves a lot of initial testings, and these come in the form of working models, smaller working models, and at the end of the day, we come down to one that we consider to be successful and working. So I'm going to try to force this to go forward. There are some details to consider. These are put together again for the first time with students, let's say, with students that are participants, because some of them again have their own office, that are not exposed to these aspects. They are, for the first time, getting to know these things. And it was used as a canopy, and at the end of the day, we like to kind of exhibit our work in different parts. There's always a working model that helps move forward with the design of the prototype. that was part of a bigger research that started in 2014 with the University of Patras, where we had another working prototype. It's an interactive, let's say, hanging canopy. But what I want to put the attention to is that these aspects are not new. The aspect of computation is not new. There's a lot of theory. It didn't come out of nowhere. There are a lot of people who have been talking about this, have written books about that. Self-organization, complexity in nature exists with various examples, as you can see. One such is, the example of flocking, birds flocking, school of fish, termite nests. They do not have a leader, let's say. They follow simple rules based on relationships, and these rules are embedded in their DNA. This phenomenon was mathematically solved by Greg Reynolds, like I was saying. His work was then utilized was published, of course, and then utilized in different ways. Usually it comes closer to the movie industry for some reason. However, as an example, the flocking behavior is based on 3 rules: separation, alignment, direction, and cohesion. It's not very visible, I'm afraid, but these are the 3 rules: is how you follow the neighbor, how you kind of like keep a distance, and how you kind of have a uniform direction, like a vector. Maybe you remember vector math from your high school class. So let me continue. For instance, in this situation, in this example, you can, let's say, define components, forces, relationships. Overall form and behavior emerge from local rules, so it's the bottom-up process. But then how can we use this design principle? And how can we realize it by taking into account material and fabrication? This is the work from 2013 in Summer Lab. So I'll talk a bit more in detail about the work of Summer Lab at the AA. I'm going to try to show by looking into 2 projects, the research on generative design, on concrete materiality, and fabrication. So it takes place at the Architectural Association. Part of it is in London, and another part is in Hook Park in Dorset. The first stage includes 2 weeks in London. The second stage is the large-scale fabrication, where we have our facilities in Hook Park in Dorset. So stage 1, design seminars, tutorials, intense 2 weeks, introducing computational tools and theories behind them. It's all about teamwork learning. Stage 2, Hook Park. This is where we scale up our prototypes. There is one large team now. We all come together as one. We learn by making, which is quite crucial for our approach. And in that sense, we have immediate feedback. It's not about contemplating, but actually making and understanding the limitations. So in 2014, there were given some design constraints. The initial design constraints were explained by the brief given to the students in the beginning of the program. So we use certain software. In this situation, this is processing, is all about scripting, is introducing, let's say, a way of writing what you want to design. That is because we can then have more control over our design decisions. And we don't have to follow software that was designed by someone else for us. Being more specific about the case study in 2014, the outcome was, this is the outcome of an investigation that was exploring earth scaffolding, fabric formwork, and concrete materiality. I hope I'm not talking too fast because I cannot see you. Okay. Right, so this was during an international 3-day workshop. The methods of realizing computationally generated self-organizing systems on a 1-to-1 scale was with the employment of a singular material system, concrete. So these methods included transmitting forces over a given distance in most effective way that have been explored by Frei Otto already. For those of you who don't know, these are representations of what we have as path systems, right towards the master. And we have different path systems, direct, minimal, and minimal detour. Not going to move forward. Right. Okay, in the context of this research, self-organization refers to form-finding methods. The amount of material of the system is decreased as its strength is increased, and these are case studies from the students in stage 1. In that sense, we're having the ability to make local adjustments according to the preferred architectonic qualities. There are various iterations that have been generated in the open source environment processing, as I mentioned. There are additional design constraints relating to gravitational forces, levels of adjusting bundle intensity on a local scale, and the ability to follow the free-form, three-dimensional shapes. Again, a lot of iterations, a lot of testing, digital testing that includes structural analysis that is conducted in software scan and solve, and eventually we rationalize it and we start to do certain analog examples. The way we use our tools in order to communicate between the team members and the tutoring team, in that case us, me, and the rest of the tutoring team, is by exporting, let's say, text files and importing them into Rhino for those of you who use the software. And then the members are given a certain thickness. I'm not sure why it stopped. But these were examples of the first stage by participants. So there you have it. You have the workflow from the design to the actual prototyping of smaller scale examples. And in that regard, we are trying to make essential the need of communicating through our tools. What came out of this stage 1, we understood that we have to construct the design with this sort of results. Shell form is selected due to its compressive properties of concrete, and then we understand which are the weak points, and then we have an understanding how we can use earth scaffolding. Hope I'm good with time. So initially, a starting geometrical form is created in a three-dimensional modeling software, Rhino, McNeil Rhinoceros, and its isocurves then in the U and V directions are extracted. These isocurves are used in the application for bundling codes and processing. So these actually were the extracted information from that software into the other software. Again, it's a matter of knowing your tools and how to use them in order to achieve, let's say, something you couldn't achieve traditionally. In this regard, we do FEA analysis in Rhinoceros with the plugin Scan and Solve, as I mentioned. And this is carried out as a solid volume analysis. The selected material properties belong to a high strength concrete. We are very specific about our inputs. We try to come close as much as possible in order to be ready for the outcome when we start to actually fabricate the one-to-one scale prototype. The FEA analysis serves as inputs, therefore, to readjust the parameters in processing. So it's kind of like a workflow back and forth. And the final iteration is the maximum neighboring, let's say, distances that have been, has decreased, let's say, the amount of bundling branches that are actually creating weak points. So we couldn't have known this just by designing it. Even just with rhinoceros. We understand it by simulating certain FEI analysis, which then comes down to how we actually fabricate it. To understand how we can actually make it, we have to also understand the limitations of our fabrication of digital machines. And in that sense, while we, let's say, rationalize the geometry and unwrap it to create the formwork, we also understand the limits of the fabrication bed of each machine. Of course, the objective is to have the final geometry sliced gradually into 12 pieces like here. Each piece is flattened like I was saying. And this flattening of non-developable surfaces is quite a challenge. We have to go back and introduce again a kind of like iteration of the code itself. So the parameters of the command are adjusted to match those of the material, while at the same time trying to adjust the software itself. It's quite a challenge. I'm going to move forward. So this is the concluding stage of 2014, stage 2. I thought I had music, but I think in the concluding stages of this process, the scaffolding for the pavilion is assembled from earth in the forest, as you can see here. So the overall form in the digital simulations are adhered to by the inclusion of timber ribs serving as guidelines during the earth scaffolding construction process that you saw at the beginning. And then the farming formwork is laid on top of it, on top of the earth scaffolding, followed by the process of concrete casting that you may have witnessed already there, held strongly in place by a period of several hours without being limited by the constraints of applying conventional reinforcing system, such as rebar. Finally, the earth scaffolding is removed and reunited with surroundings. And the outcome is actually a 2.1 meter tall, 4.4 meters wide, and the fabrication and assembly of the pavilion has been realized within a period of a week, like I said. Again, the participants vary in terms of the background knowledge. However, there was none, and there's a person in the room that can verify that, who participated here. There was no structural engineer, there was no builder, let's say. And the result is quite appealing to the surrounding. It comes close, not only as a form, but as the pattern on it. That was actually the result. It was a result of using that specific fabric that then allowed us to have that kind of impression on it, on this lovely material we all have in mind, concrete, as architects we love that. Again, these are images of that process. You can recognize the guidelines here. A lot of stitching. Some traditional tools come back. All together come as one team. Again, everyone knows what they need to do, because we are able to communicate that through our fabrication files and then sit down, talk through them. So there's one person on top. Someone knows this person probably. It's on top pouring the concrete, while everyone is kind of around helping, adjusting the process. Should I give this? So at the end of the day, there are progressive interrelationships between different simulation software. This is the key driver in recognizing the ways that we can integrate architectural criteria with the structural performance of pavilions such as this. There's a comparison that we can do between the digital simulation and of the architectural output and the final output. The pavilion itself provides useful information to be considered and embedded in the future digital simulations, so we learn from this. And there's a pedagogical approach that is engaged in this workshop aimed to establish ways of integrating the conceptual and practical aspects of these innovative design methodologies. Like I was saying, the major intention is to enable the students to grasp the theoretical, computational, and physical advantages and constraints of the described methodologies. So, this is a non-conventional way of directly connecting computational design methodologies with digital fabrication processes as part of the research agenda. I think I'm not going to talk about this. Thank you very much. Unless there is, okay. Thank you very much.